Okay, I'd like to tell you about Ampere's law, so we'll call this Ampere's law part 1. And to do that, we are going to use Gauss's law. I'm going to assume that you understand Gauss's law. We'll have a quick review of it. But let me show you how Gauss's law, if you get Gauss's law, you've laid a lot of the groundwork for Ampere's law. So Gauss's law was to find electric fields, and you could use Gauss's law for highly symmetric situations and use closed surfaces. And this is Gauss's law, and you see how we're using a closed surface integral here. We know this is a closed surface integral because these are dAs, and this little circle here means that you're going to integrate over the entire closed surface. Well, Ampere's law, we're not going to be trying to find electric fields, we're going to be trying to find magnetic fields. And again, we're going to need the situation to be highly symmetrical. And then, but here's the difference. We're not going to use closed surfaces. We're going to use closed loops. So it's not going to be a three-dimensional thing as much as it's going to be a loop, just like a rubber band is a loop, or a string that's tied to itself. So those are closed loops. A closed loop is where there's no beginning or end to the string or to the loop. But it looks very similar, doesn't it? This one has a constant epsilon naught. This one also has a constant mu naught. So this is the permittivity of free space. This is the permeability of free space. And this one had to do with what causes electric fields? Charges. Well, what causes magnetic fields? Moving charge or current. And so current times mu naught, it's very similar to Q enclosed over epsilon naught. This is the Q that's enclosed by your Gaussian surface. This will be the current that goes through the Amperian loop. The Amperian loop is this closed loop. Okay, this is B dot dl then, whereas this was E dot dA. Now notice that there is another circle here, but that's going to be a closed loop because these are dLs. So this is called a closed path integral, whereas this one was called a closed surface integral. And you know this is a path integral because it's a dl. dLs are little segments, little lengths, whereas these are little areas. So when you add up all these around a closed path, you get a closed path. Whereas when you add up all these, you're going to get just a closed loop. Okay. So let me say that all again. Then we're going to have some big, huge subscripts here at first, and then I'll show you how this applies. So Ampere's law, it's going to be mu naught, just a constant mu naught. The permeability of free space, times I. Now this I is the I through the Amperian membrane. So if we have a loop, let's say we put this is our loop. I don't mean for this to be an area here. This is just, this string that's going around here. It's got a radius r, let's say. Well, the membrane that we're talking about is, if we stretched, some material across here, that would be a membrane that covers the loop. And the only I that you want to count is the I that actually goes through that Amperian membrane. So this is the Amperian membrane. Sometimes I'll just say the I through the Amperian loop. So what I mean is the I that goes through the inside of the Amperian loop. Okay, that's going to equal the closed surface integral of B dot dl. Now that's a dot product. And that B is the B on the Amperian loop. So the only B that we're going to be concerned about are the B's that are on this Amperian loop. So like right there, what's the B right there? What's the B right there? Those are the B's that matter. And then these dLs make up the Amperian loop. And just like Gauss's law, this integral where it's going to always dissolve. It's always going to be the case that we'll get rid of the dot product. We'll pull the B out of the integral because we're going to make the argument that B is the same at every point on this Amperian loop. And then when we add up all the dLs, we're just going to get the total length of the loop. Okay, so let me show you how this is done. Okay, before I do that, I just want to remind you of how Gauss's law was done, just real fast, just one. We're going to just do a very simple, just put a positive charge here, Q. There's a positive charge Q. And then to get Gauss's law, what we did was we drew a Gaussian. If I wanted to know the field, say right here, then I drew a Gaussian surface. Now this is a closed surface, maybe it would be a spherical surface. And the field goes out in all directions from this. And I'm only drawing them in the plane of the page, but it's actually coming out at us too. And then I just write down the Q enclosed by the Gaussian surface over epsilon naught is equal to the closed surface integral of E dot dA. Now that's a surface integral. And I said, hey, the only thing that matters is the charge enclosed by the Gaussian loop. And so it's just Q, so that's Q over epsilon naught. And then I made the argument that the dot product disappears because for every dA, here's a little dA. For every dA, I'll make dA is infinitesimally small. It's radially outward, but I have to draw it big so you can see it. The E right here, then, we'll call that E. You see how the E and the dA are always parallel to one another? So I got rid of the dot product, because E is parallel to dA at every point at each point on the Gaussian surface. Okay, well, then I could pull out the E of the integral, because why is E any bigger here than here than here? Because of the symmetry, it's got to be the same. So it's going to be Q enclosed over epsilon naught, and I pull that out of the integral because it's the same at every location. And now when I'm adding up all these dAs, I just get the total area of the Gaussian surface. So that's going to be E 4 pi r squared, where this is r. And then I can solve for E. Solving for E, it's just going to be equal to. Okay, so let me show you how this works with Ampere's law then. With Ampere's law, let's have a wire going out of the page. It's coming out at us. So I'm going to just draw the cross section of the wire, and it's got a current I going through there. Oh wait, the current's going to go into the page. I drew an X, so the current's actually heading into the page. And so now, if I want to know the field, say right here, what I do is the field is actually circulating around, and the field right here is down. Using my right hand rule, I found that. Let's see. Yeah, it curls this way. Put my thumb in the direction, my right hand, thumb in the direction, it curls like that. So it's going to, I'm going to draw an Amperian loop. Now this isn't a sphere, this is actually a loop. And that should have been a circle. That's a pretty bad circle, I understand. And so I'm going to just write down Ampere's law. Mu naught I through the Amperian loop is equal to the closed loop integral of B dot dl. And then I'm going to, the first thing I'm going to do is I'm going to say how much current is going through the Amperian loop. Well, all of it is. All this I is going through the Amperian loop. So I'm just going to say mu naught times I. I'm done with that side. And that's equal to, now I'm going to get rid of the dot product, because for every point on here, B is this way, B is this way, B is this way, B is this way. The DLs are always parallel to them. These little DLs make up the Gaussian loop. So these little DLs, they're these infinitesimally small DLs, they make up the Amperian loop. So I'm going to get rid of the dot product, because B is parallel to DL at every point on the Amperian loop. And then I'm going to argue that why would B be stronger here than here than here? Because of the symmetry, they're the exact same strength. And so I can pull that B out of the integral. And so when I do, I'm just left with summing up all the DLs. Now, if I sum up all these DLs, then do you see that I just get 2 pi r? And so you can solve, bring the bring the 2 pi on the other side.